We have another result on separated sets, another important notion of separated sets. So what are we saying this time around? We are saying that if you're having a set which is a subset of set A, another set subset of B, whereby A and B are separated sets. So we have A here, we also have set B here. They are separated, A and B are separated. So C is in A, C is there, D is also in B, D is a subset of B. Then automatically C and D must be separated. We want to show that C and D are separated. So by our definition of separated sets, we show that C intersection D closure, C intersection D closure is actually equal to C closure intersection D, and this is equal to an empty set. We prove that. So what are we going to do? Since C is a subset of A, this implies that A intersection C is actually equal to C. Since C is a subset of A, then A intersection C is C. What next? So let us try to compute C intersection D closure. We have to show that this is an empty set. So this is equal to, where there is C, I'm going to substitute A intersection C. So this is A intersection C, intersection D closure. By distributive laws of intersection, this is actually equal to A intersection D closure, then intersection C intersection D closure. We have that. A intersection D closure, intersection D closure. So we are going to claim that we are going to make a claim here, a fundamental claim. So we are going to claim that claim A intersection D closure is an empty set. That claim is going to help us complete that proof. So if we are able to prove that claim, if we can prove that claim, then we are done. So we are going to prove this by way of contradiction. Suppose that A intersection D closure is actually not empty. So this implies that if it's not empty, there exists a point X in A intersection D closure, implying that this X is in A and X is in D closure, and X is in D closure. So what does that imply? This implies that X is in A and every X is in A and every neighborhood. By definition of closure of a set, we defined closure of a set in the previous session. So X is in A and every neighborhood, every neighborhood or open, and every neighborhood or open set containing, and every neighborhood or open set containing X meets D. So this implies that X is in A and every neighborhood of X meets D. What do we know about this D? This D is but D is a subset of B. D is contained in B. So this implies that X is in A and every neighborhood containing X meets meets B, because this D is in B. D is contained in B. So if we are saying that every neighborhood or even set containing X meets D, suddenly that neighborhood should also intersect with B. Should also intersect with B because D is in B. So this implies that X is in A. X is in A. No. We have X is in A and every neighborhood containing X meets B. So this implies that since A is a neighborhood, since A is a neighborhood containing X, then A meets B, i.e. A intersection B is non-empty. Since A and B meet, so their intersection has an element. A intersection B is non-empty. This is a contradiction because A and B are separated. So this implies that this is a contradiction to our original assumption that A and B are separated. So our original claim that our contradiction that A intersection D closure is non-empty is actually wrong. So this implies that A intersection D closure is an empty set. So substitute this back. I can call this equation 1. So this 2. So substitute 2 in 1. We have C intersection D closure is actually equal to C intersection D closure is actually equal to A intersection D closure intersection C intersection D closure. So we have an empty set intersection C intersection D closure, and this is equal to an empty set. So this implies that C intersection D closure is an empty set. Similarly, because you have to prove both cases, I have only proved the one direction. So similarly via the same argument, now I want you to go and confirm this. Similarly, via the same argument, C closure intersection D is an empty set. So you can prove that, because for me I've proved that C intersection D closure is empty. So you start in the same way. You just interchange the roles. So at first I consider the closure of D. Now in the second stage you will consider the closure of C. And where there is D you will substitute, since D is a subset of B, where there is D you substitute D intersection B. Then you follow the same argument. You will realize that C closure intersection D is actually an empty set. So this implies that C and D are separated.